Welcome to this lecture. In the previous lecture, we have just started the topic that mechanics of solid in MEMS and the NEMS, where we derived the equations for a straight beam in the pure bending position, where we have just studied about what is the natural axis and the curvature in the pure bending. Now, today we will discuss about some more topics, starting from the moment of inertia for the rectangular beam. Just take a rectangular beam with the height is h and the width is w. So what is the moment of inertia? I, that is y square dy, y square dA. We have already discussed in the previous that moment of inertia we have taken, that is integration of y square dA. So for this rectangular beam we can write the y square dA. dA is the cross section area of this one. So here, since width is fixed for this one, only change in the h height. So we can write y square into w dy, w into dy instead of a. So and the limit is from minus h by 2 to h by 2, because at the natural axis this is 0. So we can take minus h by 2 to plus h by 2. So after integration we will get this equation, I is equal to 1 upon 12 WH cube, and the momentum, internal momentum, that is M is equal to IE upon rho. So put on putting this value minus this 1 upon 12 WHQ E upon rho, where E is the Young modulus and rho is the curvature, radius of curvature. Next, the relation between curvature and the applied load. See first this diagram. Sorry, this is the beam in the bending position. So it's making this angle d theta. Just take a small part of this beam. So it is making a angle d theta, and this is the curve, that is value is ds. But since it's a very small part, so we can consider it as a straight line. So it may be treated as dx. Rho is a radius of this curvature, and it is this dw, it is a deviation from the initial position. So this is a deflection, we can write. So this is dw. So by the geometry we can write tan theta equals to dx upon rho. This is also rho up to this point, and so this point to this point also this is rho. So we can write tan theta is equal to dx upon rho, and also by the geometry we can write tan theta is equal to dw by dx. Why? Because this is the angle this way and then this way. So this angle is d theta, so we can write the here is angle, this is d theta, and which is 90 degree. So what will be this one? We can say if this is 90 degrees, so this is d theta. By the geometry we can just see this one, that this is d theta, so this one is also d theta, because this is also 90 degrees, it's making 90 degree with this one. So this is also d theta. So again this is d theta, so we can write d theta, tan d theta equal to dw by dx. Now for this one we can write, if this angle is this point, this section is very small, so we can take that tan theta is equal to only theta. So we can write d theta upon dx, because this is only theta, so theta is equal to dx by dp. So d theta upon dx, that is 1 upon rho. We can write d theta upon dx, this is equal to 1 upon rho, and then we can write d, because theta is equal to dw by dx, so we can write d square w by dx square. Okay, or from this one also we can write this 1 upon rho is equal to dw by dx square, or d square w by dx square. Or for the large angle, if the angle is very large, the derivation of the radius of curvature, that will be 1 upon rho. This angle is very large, this one is very large. This was for a small value, but if there is a very large angle, so we can write this is 1 upon rho is equal to d square w by dx square upon 1 plus dw by dx square whole square power 3 by 2. So this is already in different equation. From this one, in case if the deflection is of the beam is very small, this quantity is very small, so we can neglect this one because it's a square quantity. So we can write 1 upon rho is equal to d square w by dx square from this one also. So we will get the same equation, that is 1 upon rho is approximately equals to d square w by dx square. And what is the 1 upon rho? That is minus m upon ei. So we can write d square w upon dx square equals to minus m upon ei. This value of 1 upon rho from the previous equations. This is the value 1 upon rho is equal to minus m upon ei. We have already derived in the previous lectures, Bernoulli theorem. Then on integrating it, we are just starting the integration. So if we are, this is d square w by dx square, so we have to integrate it twice, 2 times. So integrating it twice, we can write double integration. First integration of this first quantity, that is m di upon dx, then again integrating it with respect to dx, so we will get this one. In the first step we will get m upon di dx plus c1, then again integrating it m upon di dx, again integrating with respect to dx, c1x plus c2, the two constant we will get. And for the cantilever beam with the tip load, value of m, that is f into l, so we can write f into x minus l here because it's changing in the length. This is change in the length, x minus l. So we can write again this, putting this value of m in this equation, we will get w is equal to minus of integration f of f into x minus l upon ei into dx upon into dx, then c1x plus c2. This is values. So step by step we are starting the integration. So what will happen? First integrating this one. So f upon ei into x square by 2, then minus lx. So we will get this equation. First again integrating it. So we will get minus of f upon fx cube upon 3 to 6 ei, fx cube upon 6 ei, this minus minus plus flx square upon ei 2 ei plus c1x plus c2. This equation we will get after integration. Then at the end condition, where the cantilever beam required that the deflection and slope both are 0, because it's a fixed point of the cantilever beam. This cantilever beam is fixed at that one point. So at that point we can take that point is x. So at that point the deflection, that's a w, that will be 0, and the slope, what is slope? dw by dx, that will also be 0. So we can write w, if w is 0, so we can write from the previous equation that if the w is 0, we can write c2 is 0 at x equal to 0. Putting the value x equal to 0, then where w is 0, so c2 is 0. But also by dividing this one, differentiating with respect to dx, we can write the equation, this one, this is flx square upon 2ia minus flx upon ei plus c1. So this equation we will get from this one, because there in both quantity x is there, so putting x equal to 0, dw by dx equal to 0, we will get c1 equals to 0. So the final derivative equation we will get that w equal to minus of fx cube by 6 ei plus flx square upon 2 ei. This equation we will get. Consequently, from the cantilever beam with the tip load, the magnitude of the downward deflection and its slope at the loaded tip are this equation. Then for the cantilever beam with the tip load, the magnitude of downward deflection and its slope are this one, these equations. So for the deflection at last point, that is x equal to l. So putting the value of x equal to l, we will get w is equal to fl cube by 3 ei in the previous equation, in this one. And also dw by dx, that is it, slope at x equal to l, that will be also fl square upon 2 ei. So these two values we will get. For the cantilever beam with the tip load, we can write the bending spring constant as this. This is the deflection, w equal to fl cube by 3 ei. So what is the spring constant? F upon W, means for the spring force F equal to kx. So what is the value of k? That is F upon x. Here x value is W. So F upon W, that is 3EI upon L cube. We will get this final. This is the spring constant for a cantilever beam. Now we will calculate the stress in the bending cantilever. Bend cantilever. To find the bending stress, we will find first radius of curvature, that we have already discussed in the previous lectures. That is radius curvature is 1 by rho equals to d square w by dx square, that is minus m upon ei. Minus m upon ei. So we can write f into, instead of m we can write f into x minus l upon ei. Where because of the minus sign we will get f into l minus x upon ei. See the previous formula. Here this is minus m upon ei. This is the value 1 upon rho d square w. So in the previous one lectures we can get 1 upon rho is equal to minus m upon ei. So instead of m we can put the value, that is x minus l. Then because of the negative sign we can write l minus x here. We have written here. So this is f into l minus x upon ei. The maximum value at the support x equal to 0, that is a fixed point, that will be 1 upon rho. What will be x equal to 0? Put x equal to 0, you will get fl equal to upon ei. So this is the maximum value of radius of curvature, that is 1 upon rho max equals to fl upon ei. Maximum strain is at the axial surface of this beam. So minimum will be center, at the maximum will be at surface. So we can write epsilon x, that is, what is the x? That is earlier we have studied, that is the value of, that is c by rho. We have studied c by rho, maximum value of epsilon x. So here where the thickness of the beam was taken 2c, here we have taken h thickness of, so the half of difference, so h by 2 rho we have written. Okay, c by rho, where thickness was c, not 2c, there thickness was, sorry, thickness was at the point but 2c. Here thickness is height of the beam is h, so we have written h by 2 into rho here. So putting the value of rho, 1 by rho, that is fl upon ei, h by 2 into fl upon ei. Then what is the value of I? So hfl upon 2e into I value is wh cube by 12. This is wh cube by 12. We have got from this equations. This is wh cube by 12 for a value of I for a beam, rectangular beam. So we have put in w by h, cancel out, this is 6 and this is h and h cube, so h square will remaining here only. So we can write 6 into L upon 2 will cancel, so upon EWH square, 6L upon EWH square multiplied by F force, because these are all dimensions, this is also constant, so taking the single and multiply by F force. So what is the value of sigma max? That is 6L upon, sorry, summation, this is epsilon max, that is strain, that is 6L upon EWH square into F. And what is the value of sigma max? Sigma max is equal to E epsilon, E young modulus. So E into epsilon value, this is. So we can write, you can cancel out E by E, so we will get 6L upon WH square into F. This is the value of stress into a bend cantilever. These are the references. Thank you.